Okay, all right, welcome everybody to Math 7280. This is a course in asymptotic and perturbation methods, which are really clever methods for finding analytical solutions to problems by exploiting the presence of either a small parameter or a large parameter. So we're going to develop these techniques through lots of different examples. I mean, it's not going to be a super rigorous course in the sense of theorems and proofs. It's not that style. It's going to be a very applied math, physics style course with lots of examples, explicit calculations, use of computer, hopefully some applications to science and engineering. I'll throw those in when I can. But mainly it's a math course where we're going to be trying to develop these approximate techniques by applying them to various integrals that depend on either a small or large parameter, or ordinary differential equations, or towards the end, we'll do some partial differential equations also. So that's pretty much it. I mean, let's just get started. All right. Oh, actually, maybe before we get started, I should just say I'm going to use a textbook throughout, and I'll be assigning you homework to do from Bender and Orsog. This is my personal copy. You can see it's been through the ringer. Been using it for years, and it's really a fantastic book. I would recommend buying it if you have a chance. Although, if you're a Cornell student, you have free access to this book through our library. So you can just download a copy off the internet for free. You wouldn't even be pirating it. We have a site license to Springer Verlag, and it's now available for free from them. So I'll frequently refer to it as B&O or BO, Bender and Orsog. There's also some other books that I'll occasionally mention that you could find helpful. There's one by Michael Greenberg that actually I'm going to reference today in an example we're doing. There's a nice book by John Hinch from Cambridge, Perturbation Methods. And Mark Holmes from RPI wrote a nice book, Introduction to Perturbation Methods, which I think you can also get for free on our Springer site license through the Cornell Library. Okay, so those are the books. And let's just start with an example. All right. Okay, so we're going to begin with the concept of asymptotic expansions. All right, and to get that going, rather than giving you a definition up front, let's just do an example, and you'll see the idea of an asymptotic expansion emerging very naturally from this example. So let's consider an integral that depends on a parameter. I'll call it x, the parameter. So the integral we'll do is regarded as a function of this parameter. F of x is defined as integral from 0 to infinity of, let's see, e to the minus xt dt, and in the denominator, 1 plus t. So you see x is playing the role of a parameter. We're integrating with respect to t over the whole positive part of the real line. And so we're going to fix a value of x. Just regard x as some positive number. At this point, not necessarily large, although later we're going to let it be large. If you're familiar with Laplace transforms, you might recognize that this kind of thing would come up as a Laplace transform, except usually it would be called e to the minus st, but here I'm calling it x rather than s. But okay, so it's a Laplace transform of the function 1 over 1 plus t. And the reason we're looking at this with an asymptotic method is that you cannot evaluate this integral in closed form in terms of elementary functions. So this cannot be evaluated in closed form in terms of elementary functions. When I speak of elementary functions, I'm thinking here of like polynomials, sine and cosine, e and log. That's pretty much it. I guess power, maybe fractional powers would be okay too. But anyway, so this thing, if you pop it into Mathematica or Maple or your favorite symbolic manipulation program, it will give you something in terms of a so-called exponential integral that's defined in terms of this integral here. But I'm not going to presume you know about special functions. Actually, a lot of this course will be about asymptotics of various special functions, things called parabolic cylinder functions, Bessel functions, Airy functions, all this really great stuff from the 19th century that people don't really remember so much anymore, but comes up a lot in applied math. Anyway, we're going to do asymptotically. Sorry, was there a question or comment?
Physicists do know about Bessel functions and Airy functions all the time.
Of course, of course. Right, good point, Andrea. That's right, sure. In physics and engineering, Bessel functions are not very exotic. They come up as eigenfunctions for problems with cylindrical symmetry or radial. I mean, yeah, absolutely. We see Bessel functions all the time in polar coordinate problems and cylindrical. But okay, sure enough, right. So this is not just exotic stuff. All right, anyway, so now let's just try to understand how this integral behaves for a large x. Or, I mean, a naive thing you could do is try a series expansion of the that expression in the denominator. Let's try writing, to make progress on this. Let's write 1 over 1 plus t as 1 minus t plus t squared minus t cubed, et cetera, expanding it as a series like this. Now, keep in mind, this series only converges for small t. Specifically, this series converges if t in absolute value is less than 1. But let's just ignore that temporarily. I mean, as you can see in the integral, we're integrating over the whole real line, the positive part of the real line from 0 to infinity. So if we replace this expression with the series, you could imagine we'll get into trouble because we're using the series outside its range, its region of convergence. But let's not worry about that for the time being. So what would happen if we pop the series in there? So we're going 0 to infinity, e to the minus xt, and then, as I say, just replace the other expression with this series and integrate term by term. Really Wild West style here. Now, each of those terms can be evaluated exactly. Powers of t times e to the minus xt, you may be familiar with that. There's an identity for those. I'll just write down the answer and then I'll remind you what the identity is. Well, actually, let's put it this way. This comes out to be, after we do those known integrals, 1 minus x minus 1 factorial over x squared plus 2 factorial over x cubed minus 3 factorial over x to the 4th, et cetera. So what I'm using here is the identity that if I integrate t to the n, e to the minus xt dt from 0 to infinity, that actually gives you n factorial over x to the n plus 1. So if you've ever had practice with something called the gamma function, this might be familiar to you. Or if you haven't run into the gamma function, you can simply derive this by just doing integration by parts, or by differentiating under the integral sign, if you know that trick. So there are various ways to derive this. Maybe I'll leave that to you to check. So it can be derived by repeated integration by parts, or by differentiating under the integral sign, as a wonderful trick that a lot of you would know. What I'm saying there is, like, you could just calculate the integral for e to the minus xt dt. That's an easy one. Forget about the prefactor of t to the n. Just do e to the minus xt dt, do that integral, and then differentiate both sides of the result with respect to x. Keep doing that over and over, and you'll keep pulling down factors of t from the exponential. So by differentiating under the integral sign with respect to x, we'll give it to you. Okay, so anyway, using that identity repeatedly, you get this expression for f of x, where you see now we've expanded f in terms of some kind of series. Maybe I should pause here. Is there any question at this point?
Why are you allowed to exchange the summation and the integral?
The question was, why am I allowed to exchange the summation and the integral? This is the spirit of what we're doing. We're not rigorous at all, and probably we're not really allowed to exchange them in this case. Because after all, this series that I've written down, I'm using in a region where it doesn't even converge. So everything I'm doing is completely, well, probably completely wrong. The word I want to use is formal, meaning I'm just shoving symbols around. I'm not being careful at all. So there is no rigorous justification for that interchange of integral and summation, in fact. I'm just doing it to make a certain calculation. We'll see that we get some weird stuff out of this result because of the bad behavior we're exhibiting. Was there another question? I won't be so loose throughout, don't worry. But for now, I am. Okay, so let's continue. So anyway, I get this formal expression for f of x. And you could ask, I mean, does this series converge? And the answer is no, it doesn't actually. Well, let's check. Let's try doing it with the ratio test. That would be an easy way to do it. I mean, by this series, I'm referring to this one up here. Okay, so does it converge? Well, so let's look at the nth term. Maybe I don't really need to stay there in red, but so the ratio I could look at is a n plus 1 over a n. And remember, the ratio test is you're supposed to look at the absolute value of that and then ask, does that become less than 1 as n goes to infinity? So let's check if it does. So the an in this case for our series above, just consulting it again, is of the form, it looks like n minus 1 factorial over x to the n. By the way, these lectures will be posted, so if you don't want to take notes, you can just watch all this later. But if it helps you to write things down, then go ahead and
with alternating sign, but I guess that doesn't matter here because we're taking the absolute value.
Oh, that's right. Let me say the absolute value of an. You're right. That's right. So the absolute value of an is that. And so then if I look at the ratio, let's clean that up a little bit. We're going to get, so n factorial over n minus 1 factorial, and we have x to the n, and in this denominator we have x to the n plus 1. And so lots of cancellation, that ends up being just n over x. And so you can see this ratio. Now, let's think about what we're holding constant and what we're letting go to infinity. Remember, we're thinking of x as fixed. Pick some value of this parameter x greater than 0, and now let n go to infinity. And you can see that, in fact, this ratio is certainly not staying less than 1. In fact, it's becoming infinitely large. So the ratio test fails miserably. And this tells us that this series that I've written down with my formal manipulations diverges. In fact, it diverges for all x. So I've just written down a divergent series. Now, in elementary calculus, you're sort of taught like that's the end of the story. When something diverges, you're done and you just stop. But we're going to find in this course that divergent series are extremely useful, which might surprise you. And actually, in some ways, they're more useful than convergent series. It's kind of wild. The fact that they diverge is not going to cause us much trouble because we're usually not going to take infinitely many terms. We're usually going to just take one term, the leading term in the series, or maybe one or two, or just a very few. So divergence is not going to cause us much trouble. But we are going to see a lot of divergent series. So, okay, well, anyway, so the series diverges for all x. Now, from a traditional point of view, you might feel like, oops, I've just made some kind of, problem. And we're not surprised that we're getting punished for, I mean, if you want to think of it as punishment, it's not really, though. It's kind of our punishment for using, as I already telegraphed, I'm using this expansion in a region where it's not valid. Using that outside the radius of convergence. Okay, well, nevertheless, let's not give up on this series because it's got some interesting lessons for us. Right. So at this point, we might quit, but let's not. Let's look at what the series predicts. So nevertheless, let's look at what the series predicts for some moderately large value of x. I don't know. Let's say for x equals 10, which is big, but not gigantic. So the first four terms, if we take those, 10 is a convenient number because powers of 10 are very recognizable in decimal. So the first four terms would give us, so we had 1 over x, that will be 0.1. Let me write 4 digits. Then we have minus 1 over x squared. So that'll give me minus 0.0100. Let's say the first four terms. Then there's 2 factorial over x cubed. So that's giving me 0.0020. And then the next term would be, it's 3 factorial, that's 6 over x to the 4th. So 0.0006. And if you add that up, you get 0.0914. So that's our prediction for f, that this integral that we're trying to understand, evaluated at x equals 10. Now, you can actually evaluate that integral in a computer with like I say, Mathematica or any numerical quadrature method that you want to use. In fact, what do we find for f evaluated at 10? If you do it exactly, well, numerically exactly, f of 10 comes out to be 0.9156 or so. So that's supposed to be encouraging, that without doing very much work, didn't need to do any numerical integrating or anything, we have a pretty decent approximation. I mean,
Aren't we missing a zero after the comma?
Sorry, Marie, I couldn't quite hear you there.
Aren't we missing a zero after the comma for f10? Because otherwise it wouldn't be a good prediction.
I'm sorry, I still didn't hear. What did you say about zero?
So when you're calculating f10, shouldn't it be 0,0915? I'm just saying there might be a zero.
Zero comma.
You're off by an order of magnitude.
Did I lose? Oh, I'm sorry. Of course. I'm sorry. Right. I put my decimal place in the wrong place. Thank you. Yeah, that's what I meant. I'm sorry. Yeah. Good. Thank you. Good eye. I appreciate the corrections. That's what I meant. I mean, you agree that's right, right? If I did the subtraction correctly. Yeah. Yeah, that's working. Okay, good. So say using numerical quadrature. Other comments or questions at this point? Okay, so that's telling you that there's something sort of right about what we did, even though it seems extremely sloppy and hard to justify. All right, so let's try to understand why did this work as well as it did. Why was this so successful? I mean, or to put it another way, how could a divergent series give such good results? Okay, so now let's try to put on our analysis hat for just a minute and try to think about this more carefully. Let's use the language of partial sums and remainders. So let's say Sn of x will be the nth partial sum. Meaning I'm going to sum the first n terms. So from k equals 0 up to n minus 1, minus 1 to the k to take account of that alternating aspect of the series. And then the individual terms are k factorial over x to the k plus 1. Okay, so that's the sum of the first n terms. And if you rather just write it out, that would look like 1 over x minus 1 factorial over x squared plus 2 factorial over x cubed plus dot, 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 up to the last term that we have is minus 1 to the n minus 1 factorial over x to the n. Okay, so that's our nth partial sum. And then the remainder is going to be everything else in f of x after we subtract off Sn. So let's let Rn of x, the remainder term, define that to be f of x minus Sn of x. By the way, so when you're looking at Bender and Orsog's book, they use different notation for this. So they would call it epsilon n of x. And they might also refer to it as the error term, epsilon for error. But anyway, either way. So we got this remainder term, and you can think of it or interpret it as this is the error we make in approximating f by the remainder, the error we make by stopping at the nth term. Okay, now what we would like to do is estimate the remainder because we want to see, how close are we getting to the exact answer, which at the moment is still an unknown number. So let us estimate the size of the remainder term without calculating it exactly. So let's deal with the f more carefully now. I say more carefully, what I mean is not be so freewheeling about the infinite series expansion we used earlier, but just use a finite geometric series and then take care to include the correct remainder term in that. In other words, let's write 1 over 1 plus t as 1 minus t plus t squared minus t cubed plus dot, 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 and then out to a term which is plus minus 1 to the n minus 1, t to the n minus 1. Put all of that inside a big square bracket. And then plus a term which is minus 1 to the n, t to the n, all over 1 plus t. So what I'm doing there is, that's exact. There's no approximation in this formula. All I'm doing here is I'm just using the exact sum of a finite geometric series. Right. If I took, in other words, look at the thing in brackets, the square bracketed expression. That's just a finite geometric series with a ratio -t between consecutive terms. And so you can write down the exact sum of that using the trick that Gauss discovered when he was 5 years old or whatever that story is. Right. So using the exact sum of a finite geometric series. Yeah. Okay, so that formula is exact, and why that's helpful for us is that now when we do our f of x properly, we can estimate the remainder term from this leftover piece at the very end of the line above. So our f of x is now going to be the integral from 0 to infinity of all the stuff that was in the square bracket, which we had treated very formally earlier, times e to the minus xt dt. And then plus, so this is just going to give us what we earlier called Sn of x, the nth partial sum. When I integrate all those terms in the finite part of the series. But then the interesting part is this next part, integral from 0 to infinity of this additional term, minus 1 to the n, t to the n, all over 1 plus t dt. Oh, sorry, and I have to say times e to the minus xt. dt. There. That looks good. And so that stuff is by definition the remainder. Still with me here? Good, we're good, no questions? Okay, so now we get to put on our, like I say, our analysis hat and try to understand the size of Rn of x. Okay, so let's do that. Rn of x in magnitude, well, I can get rid of that minus 1 to the n term, since I'm just looking at sizes here. So 0 to infinity, bunch of stuff over a denominator, over a division sign. So t to the n, e to the minus xt, over 1 plus t, dt. And now, the crude way to estimate this, but it's good enough, maybe you have an idea. I don't know, you want to suggest something that you might think of doing? I mean, if I want an upper bound on Rn of x, right? So I want to say that this is definitely less than something.
You could exclude the denominator, and that would be an upper bound.
Sorry, what was that again?
If you just exclude 1 over 1 plus t.
Yeah, because, right, 1 over 1 plus t for t greater than 0 is always going to be less than 1. Right, that function 1 over 1 plus t is just decreasing from 1 at 0 monotonically down to 0 at a t equals infinity. So yeah, as you say, let us just upper bound that term by 1 itself. So this is actually strictly less than, if we're a little more careful, we could, you know, it's definitely strictly less than this, where we're using the fact that 1 over 1 plus t is less than 1 for positive t. And so those integrals, I mean, we already know how to do those. I mentioned them earlier. These are just equal to n factorial divided by x to the n plus 1. So there's our estimate. Now, what's interesting is that that's the next term in the series. Right? When we had written out the series, it was a bunch of expressions, you know, that look like this. So in fact, what we're showing is that the remainder term is less than the first term that we neglected. Let's make that little comment that the remainder or the error term is smaller than the first neglected term. In the infinite series. So if you want, we could say it this way: Rn, the remainder term at the nth stage, is less in magnitude, or certainly less than or equal to, if we want to say it like that, an plus 1, what I had earlier called the a's. Okay, so that's interesting. And that, because remember, this is a strict estimate on the size of the error. And so we can say things like this. What if we had taken one more term The next term that we didn't take, remember we stopped at, I think, 10 to the, there was a denominator of 10 to the 4th. It was a 3 factorial over 10 to the 4th. So if we had taken the next term, which would be 4 factorial over 10 to the 5th, which, if we want to see how big that is, that's 3 zeros and then a 24. If we had taken the next term, we would have been able to conclude, or we would see, that in terms of our notation with partial sum, the partial sum S4 of 10, which is 0.0914, that's as far as we went, that must lie within a distance of 2.4 times 10 to the minus 4 of the true answer. 4f of 10. So we still don't know the exact value of f of 10, but we do know bounds on how close we are. All right, so this raises the natural question. I mean, you tell me, what would you think of asking at this point? You may have to unmute yourself if you want to say it out loud.
How many terms should you use?
Yes, how many terms should you use is a natural question. Right, thanks, Jackson. Right, so that is exactly the question. Where's the right place to stop? How many terms should we take? And the principle is you want to get as close as you can to the right answer, you know, for optimal accuracy using this kind of approach. Well, so for that, I've prepared something that I want to show you. I'm not sure where I put it on my notability here. I think I have some blank pages in the way. Wasn't sure how much writing I would need to do. We can come back to all that. Wow, that's a lot of blank pages. Okay. Anyway, here's a little table. So I mentioned earlier that we would be using Michael Greenberg's book. He computed this on page 45 of his book. And so let's take a look at this table. What he's showing here is the size of the individual terms. Hope that's big enough for you to be able to see. The first term was 1/10, right? The next one was 1/100th, but with a negative sign in front of it. And you can see that the terms are getting progressively smaller as we go down, but not forever. Remember when we did the ratio test, we found a cutoff where n was the same size as x. So since we're interested in the number 10, we're looking at f of 10, we would expect that once we look at more than the 10th term, they're going to start getting bigger. This is what's causing the divergence, right? Instead of the terms progressively getting smaller, they're starting to get bigger after a certain point. So if you look here at the 10th term, it's got 4 zeros and a 3. The 11th term also has 4 zeros and a 3, but after that it says 9, 9, whereas this one says 6, 2. So they're starting to get bigger, right? 4, 7, 6, 2, 8, 7. So we should stop somewhere around the 10th term. Still, we can estimate errors using the fact that there's alternation. It's interesting. Let me make this little remark that since the the remainder terms, we know if we include their sign, they alternate. Since Rn of n alternates with respect to n, the exact value of f of x must lie between any two consecutive partial sums. Similar to the things that you use when you're proving properties of the, there's an alternating series convergence test that we teach in first year calculus. The reasoning that leads to this conclusion is the same as what you use there, except the interesting thing is that this result doesn't require convergence, what we're saying here. This holds even though the series doesn't converge. I'll show you why in a second. So let's see why this still works quickly. Just a little check. And then we'll come back and see what the optimal prediction is from our work earlier. So just a tiny proof of this little fact. We know that f of x is, on the one hand, the nth partial sum plus the nth remainder, but it's also equal to the n plus first partial sum plus its remainder. And, but let's say we're at a place where the Rn was positive, but then the next one is negative. Then using that fact tells us that our f of x, because the Rn is positive, that means that f of x is greater than Sn, but f of x is also less than Sn plus 1, right? Because in one case you have a positive thing being added to the s, and in the other a negative. So the f is trapped between those two consecutive ones. In this case, it's between Sn plus 1 above it and Sn below it. So just knowing about the partial sums, they're coming in like a vice around the true answer, until, as we saw, at some point, the vice starts to expand again, right? So you want to go to where the vice is as tight as possible. And so if I go back to Michael Greenberg's table, then here are the consecutive partial sums in the right column. And so let's look at them. Here we've got, well, I mean, we know the right answer is in between any two of them. So like say, whoops, let's do that with this thing. Between 9164 and 9152. If I stop down here, it's between 9158 and 9154, which is pretty good because we know the exact answer is about 9156. We mentioned that earlier. So it's really doing pretty well if you use these two and split the difference. Anyway, all right. So just to summarize what, we're pretty much done with this example, but to finish it off, we should stop where the partial sums are tightest. And if you do that, so that corresponds to n equals 10, you can then conclude that f of 10 is between those two partial sums that we see there, 0.09154 and 0.091582 or so. Actually, I feel like we could have done better than that. Why not 5.6? Oh, I see. No, I guess not. Right here, I see 5.4 and 5.8. Okay. So that's all I want to say about that example. Hopefully it's given you some feeling for divergence series could be your friend, unlike what you might have been taught previously. Is there any question before we leave it? Okay, so I want to use this. By the way, if you feel uncomfortable asking out loud, you could always type something in the chat and I could see it there. Let me look at the chat and see if there's anything. But there is not. Okay. All right. So with this in mind, let's now get a little more general. I think actually at this point. Oh, yes, please.
So is there a way to compute where the partial sums are tightest without actually numerically computing this?
Where the partial sums are tightest without actually numerically computing this.
Isn't it where the exponential and the factorial intersect each other? And
with respect to n, yeah, and find out where it's equal to 0.
Say that again?
You can differentiate with respect to n.
Treating n as if it were a real number?
Yeah, and then find the optimum.
I see. So find the tightest, the smallest remainder term. I mean, you're using the estimate of the remainder term as if it were the true remainder term, and then look for the smallest estimated remainder term. That would give you something.
Makes sense.
Yeah. Okay, but so I did want to just make a little comment before I get into my definitions. So various comments. This series that we wrote down, I mean, I said it was divergent, 1 over x minus 1 factorial over x squared plus 2 factorial over x cubed, etc. That thing clearly provides some kind of useful approximation to f. Okay, but I mean, certainly at least for large x. But it's not a convergent series, as we keep saying. Instead, it's what's called asymptotic. Okay, so I want to try to define what that means. And so to do this, if you want more careful statements than what I'm about to give, you could take a look at Bender and Orsog. Look at pages 78 and 9, and also 118 to 128. And that gives you a lot of treatment. But let me just hit the high points here. So I'm going to build up to the idea of what we mean by an asymptotic approximation through a series of little definitions. Okay, so the first one is this symbol, which is the asymptotic symbol. We'll say that a function, so you read this as f is asymptotic to g. Where usually the function f is going to turn out to be something usually that will be hard, actually, or difficult or complicated. That is, like in this case, we were trying to approximate a complicated integral by a simpler expression. So usually you have some kind of complicated thing, and then this will be something relatively simple. And what it means to be asymptotic is, first of all, this is supposed to be a statement as some parameter approaches some base point x0, which in our example was x was going to infinity, though we didn't really realize it. But so when we say f is asymptotic to g as x goes to x0, what that means is that if you look at the ratio between them and take the limit as x goes to x0, that ratio is 1. So that's what we're going to mean by asymptotic, that the ratio of the two things approaches 1 as you approach some point of interest. As little examples of this, let's say, I mean, you probably know a bunch of examples. Classic one is the small angle approximation in physics, that sine of x is approximately x for small x. So what we would say here is that sine x is asymptotic to x as x approaches 0. And that's true because of that famous limit, that limit of sine x over x is 1 as x goes to 0. So sine x is asymptotic to x in this sense. Similarly, you could say sine of x is asymptotic to x minus x cubed over 3 factorial, because that would also have a limit of 1 as x goes to 0. But I want to make one little kind of niggly point that you should be aware of in the notation. If you're kind of a warped person, you might be thinking at this moment, well then sine of x is also asymptotic to x minus 117 x cubed as x goes to 0. Or some other absurd number in front of the x cubed, because that ratio would go to 1, right? I mean, after all, when x is very small, x cubed will be negligible compared to x. So this is true technically, but sort of stupid and not the way we would ever use the asymptotic symbol. So when we write an asymptotic symbol like this, it's kind of understood that all the terms are supposed to be correct. So I would say we never write this hopefully we never write something like this, since, I mean, in order to justify using the symbol, you should also have the, if you subtract the x and then divide by, say, in this case, you know, the silly 117x cubed, that ratio, or maybe I should be writing negative, that ratio does not go to 1 as x goes to 0, because I have the prefactor incorrect, right? It's only when I have the correct prefactor of 1 over 3 factorial that it would approach 1. So the lesson here is, if we're going to include more terms in an asymptotic expansion or an asymptotic approximation, so if we include 2 or more terms, all of them are supposed to be correct in the sense of this example. I can say that more precisely, but I think you get the idea of what I'm driving at. I see something going on in the chat here. Okay, someone had to leave early, no problem. Okay, so, all right. So let me move on to my second definition. So that's the idea of asymptotic. Is there any question about this? Okay, so let's go on. The next one is the big O symbol, which you may have run into in various courses, including in computer science. So this is pronounced big O. And it's a useful symbol. It's closely related to asymptotic, but it's a little less precise. So this means that if I look at the ratio f of x over g of x, it means this is bounded as x goes to some point. I mean, we're always taking f of x is big O of g of x as x approaches some point x0. If this ratio stays bounded as x approaches x0, meaning it doesn't blow up, it doesn't become infinitely large, then we say it's big O. And where that is useful is if you're not interested in prefactors. If you're just interested in orders of magnitude, then big O is helpful. So if we don't care about getting the prefactor right. So just as examples of that, you know, how that kind of terminology would be used, we could say in the same example, f of x equals sine x is big O of x as x goes to 0. Notice, by the way, I'm not using the tilde symbol. I'm not using the asymptotic symbol. I actually write equals. So don't mix the two notations. Don't write tilde big O. They're separate symbols. So you write f of x equals big O of x. Or you could say something like, you could say sine of x is x plus big O of x cubed. That would be correct. Because sine of x minus x over x cubed is bounded as x goes to 0, which you could check by L'Hopital's rule, or just knowing the series expansion for sine for small x. Okay, so that's the big O notation. And then there's also little o notation. I'll try to make my big O much bigger than my little o so you can tell the difference. And Bender and Orsog write this a very suggestive way, which I'll be doing throughout the course. They write this as f of x is much less than g of x, with a very precise meaning as x approaches some point x0. So they're equivalent notations, little o or the much less than symbol. This means that the ratio of the two approaches 0. F of x over g of x is 0 as x goes to x0. So in that sense, f is much smaller than g near that point x0. So in this, as an example of this with our sine function, you could say sine of x is little o of 1 as x goes to 0. Right, because sine of x over 1 approaches 0 as x goes to 0. So, you know, other ways you might say it is f tends to 0. I mean, where this will come up is that it means f tends to 0 faster than G does. That's one way you can have this kind of property, that F is getting small faster than G is, or G tends to infinity faster than F does. You could have those are two different ways that you could have F much less than G. Okay, so with all those things in mind, I've now pre-written, because it's so much writing, the real money definitions that we're going to need, which are these last two. So this is the concept of an asymptotic sequence. So we'll say a sequence of functions, phi j of x, is an asymptotic sequence if, as x goes to x0, if each term is much less than the previous term in the asymptotic sequence as x goes to x0. So as an example, think about the functions. All these functions are going to 0 as x goes to infinity, but they're ordered in this way. This one goes to 0 much slower than this one, which goes to 0 much slower than this one, right? These are different decay rates. So this is a way of formalizing. You've got these different functions decaying at different rates. And so in terms of that, because these tend to be the sorts of objects that appear in asymptotic expansions, like we saw with our expansion of the integral. This leads us finally to what we were aiming for today, the concept of an asymptotic expansion as introduced by Poincaré back in 1886. So it's in terms of what we just wrote down, an asymptotic sequence. You say that a function f, if you want, think of our exponential, the integral that we did. Function f of x has an asymptotic expansion written this way. F of x is asymptotic to some coefficients, a1 times a function phi1 plus a2 times a function phi2. Oh, that should say phi2. Plus, et cetera. There's an infinite series of these functions. This is an asymptotic expansion of f in terms of this asymptotic sequence of phi's, if the phi's really are an asymptotic sequence in the sense that I just defined above, and if you have this property in the red box, that when you take the partial sum, that's what this is, right? Recognize what we're doing here. We're summing up the first n terms in the asymptotic sequence with appropriate prefactors. So if you sum them up, you get this partial sum up to the nth term, subtract that from f, this thing we would consider is then the remainder term. So if the remainder term is much less than the next, or than the last term in the sum, that's what you mean for an asymptotic sequence, that the error is much smaller than the last term you've included. So equivalently, in terms of this partial sum notation, what we're saying is that the remainder at the nth stage is much less than the nth term. So that's what I've said in words there. Also, you can check that this will imply that the remainder is big O of the next term. The error is of the order big O of the first term that you didn't include, the first term neglected. So an example of all this is what we just did. I mean, we did all of this without realizing it. When we expanded that integral and we got this expression for it, we were actually deriving a genuine asymptotic expansion of that integral. So it's valid to write this in the sense of asymptotic expansion. To check that it really was an asymptotic expansion, what do you have to do? You have to check that these are terms in an asymptotic sequence, and they are as x goes to infinity. And you have to check that condition on the remainder term that is in Poincaré's definition. So the remainder term is less than this, we showed, but that is itself much less than this term as x goes to infinity, because this is decreasing much faster than this. It's got an extra power of x for any fixed n. And so it is true that the remainder is less than or equal to this next term. So yes, check, that worked. Okay, so I wanted to conclude with just showing you some Mathematica results for this little problem. Let me stop sharing this screen and share a different screen. Let me share what's on my desktop just for a second, and then we'll quit. I do recommend that you use Mathematica throughout this course. Cornell has a site license for Mathematica, so you can buy it, I think, for pretty cheap, like on the order of $20 for the year. And you probably should do that if you haven't already done it or don't have access to it. It's really worth learning. So what have I done here? I'm doing the case of x equals 1 rather than x equals 10. And I just wanted to graph the various functions that we've been talking about today, 1 over 1 plus t. I mean, what's really going on in this integral? We had a decaying function 1 over 1 plus t, which we were then multiplying by this exponentially decaying term, e to the minus xt, this orange term. Together, their product makes this green term. And in effect, we were looking at the area underneath the green curve. That's the integral we were studying as a function of x, where x is the decay rate of this exponential. So if the exponential decays faster, we're going to have less area underneath the green curve, which is why the whole thing is a decreasing function of x. So I asked Mathematica to integrate the expression that we've been studying, e to the minus xt over 1 plus t, integrated it over the whole positive real line from 0 to infinity. I gave it the assumption that x was greater than 0 so that the integral converges. And it tells me, as Mathematica is able to do, exactly what special function this integral is. It's negative e to the x times something called the exponential integral EI function. E for exponential, I for integral, of negative x. Now, I don't know much about that function, so I just define f of x to be this thing and ask Mathematica to plot it. And you see it's some decreasing function of x. Now, our asymptotic expansion said it should be approximately 1 over x. That's the first term in our asymptotic expansion. And you see 1 over x is doing a pretty good job of hugging the actual function f once x gets big enough. Out here at x equals 10 is where we did the calculation, and we were getting that number 0.09, whatever. But you can see it's not great when x is small. But then again, we only took one term, 1 over x. We know for out here at x equals 10, we should really take 10 terms if we want a better approximation. Incidentally, if we go out to bigger x, now it looks pretty respectable. The 1 over x approximation does pretty darn good job of matching the complicated exponential integral once x gets large, right? So this is the power of asymptotics. Incidentally, and I'll stop with this, Mathematica knows how to do this course. I mean, you could say, why are you even taking this course now that you have Mathematica? Well, because you don't necessarily just want the answer, you also want concepts, right? I mean, you want to understand what's going on. And there are a lot of other justifications for why you should take the course. But still, give Mathematica its due. You can compute the asymptotic expansion like this. You say, take the series of f with respect to x, but expand around the point at infinity. Expand at x equals infinity, right? That's what we said. This is asymptotic as x goes to infinity. And then just give me one term. Well, it gives me 1 over x, which is the correct first term. I could say, no, actually, I meant for you to give me 5 terms. And there it is. Those are the first 5 terms that we cranked out laboriously with our, n factorial integral. But so it knows how to do all that. And you can ask it to plot, say, the first 3 terms to see if that does better. And, you're getting a pretty good asymptotic approximation. Oh, well, all right. That's probably a good time to stop. My phone is ringing. Excuse me. stop that. All right, so I think I better quit there. Is there any question before we adjourn? All right, well, thanks a lot. So next time we'll look at some other techniques for asymptotically evaluating integrals. That's what's going to occupy us for the next few lectures. Okay, see you then.